So in this video, I will be explaining basics of quantum computing, and here I am trying to answer the question of what is meant by a quantum bit. So in order to explain what is meant by quantum bit, uh, I will be comparing the quantum bit with our classical bit. The classical bit and quantum bit are both used to represent information in computers. So the way in which we represent the information is different for a quantum computer and our conventional digital computer. In a conventional digital computer, we represent the information in terms of zeros and one, and this we are calling it as classical bit. These are nothing but two different states that are used to represent the information, which is either true or false. So, in case of the quantum computer, the quantum bit takes three different values. The first value we are calling for time being, it is called as quantum bit 0 or qubit 0. The second value that a quantum bit takes is the qubit 1, and the third value that a quantum bit takes is a function of two different bits, qubits. First is the qubit 0 and qubit 1, and qubit 0 and qubit 1 has two coefficients associated with it. We are calling it as alpha and beta. So this is the third state, which is very much different from the classical bit. Classical bits never takes such a combination state or a super this combination of two different bits. So here the alpha and beta are the coefficients that are associated with qubit 0 and qubit 1, and this alpha and beta takes the values from complex number. So alpha and beta, the values of the alpha and beta are from complex domain. They take the complex numbers like 3 plus 5 times I. So this is a complex number. So alpha and beta takes the values from complex domain. One more condition needs to be satisfied with respect to uh, quantum bit's valid state. So if this the square of alpha square, the absolute square of alpha and absolute value square of beta should always come equal to the 1. So this condition needs to be satisfied in order to a qubit in a valid state. So these states 0 and 1, qubit 1 and 0 are also known as pure states, whereas the third state, that is the alpha times qubit 0 and beta times qubit 1, is known as superimposed state. So now in qubit, there are two different types of states. One is pure state, which takes two different values, qubit 0 and qubit 1. And the third state, which is calling we are calling it as superimposed state, it takes the value of alpha times qubit 0 plus beta times qubit 1. In addition to that, norm of alpha square and norm of beta square should be equal to 1. So this is the difference between the classical bits and digital classical bits and qubits. Classical bits takes only two values, that is 0 and 1, and quantum bit takes three values, two are out of two values are pure state, qubit 0 and qubit 1, and third state is the superimposed state. So this is about the quantum bits. Now let us see what is the purpose of superimposed state versus the pure state. See, in case of the pure states in conventional digital computer, pure states or the qubits are typically used to encode the information. Suppose that, for example, we want to represent the result of a student appearing for an examination. So the result may be either pass or fail, which we can denote in classical way, bit 1 and bit 0, or here qubit 1 and qubit 0. In case of the superimposed state, let us think that examination is going to be conducted and student is appearing for an examination. We have not, the result is not yet out. The result of that students appearing for an examination is that either it is expected that the student may, there is 60% of possibility that student may pass in the examination, and 40% is the probability that student may fail in the examination. If this is the case, then we can represent that situation with the help of a superimposed state, where we are meaning that there are 60% chances are there that student is appearing for a passing the result, passing the examination, and 40% is the possibility that student may fail in the examination. So this is the one way in which you can encode this information through superimposed state. Now let us take another example of pure states. Suppose that you have invested certain amount in the stock market, and you have realized your profit or loss. So then if you have got the profit, then means that you can represent that through state qubit 1, or loss, if you are experiencing loss, then that is the qubit 0, or in conventional way, that is bit 0 and bit 1. Now suppose that you have some unrealized income, or unrealized, you have not you have not yet realized your profit or loss, and there is the possibility that 35% possibility that you may get some profits, and 65% is the possibility that you may experience loss through your investment. If you want to capture this situation, then you can use the superimposed state. Like suppose that the third example is that today you are experiencing today's climate condition. It may be either sunny or cloudy, which you can represent through two different states, 1 and 0. Suppose that you want to represent, you have not measured the today's climate, and you want to represent, either it may be 25% probability that the climate may be sunny, and 75% is the probability that climate may be cloudy. So this is the significance of the superimposed state. If you are, if there is some uncertainty is in there, and you can represent that uncertainty through superimposed state by associating some coefficients in terms of alpha and beta to the states, qubit state 1 and 0. Now here we are going to visualize a qubit through a block sphere. A block sphere is a sphere having a radius equal to 1 unit, and this sphere has a north pole and a south pole. Then the upper portion of the this is the upper portion of the sphere, and this is the lower portion. This is the lower portion, and this line that divides the sphere into two equal parts that is called as equator. Now the qubit 0 is typically is the north pole of the sphere having radius 1, which we are calling it as the Bloch sphere, and the qubit 1 is the south pole of this Bloch sphere is the qubit state qubit 1. So this is the positions which we can use visualize a qubit 0 and 1 on a Bloch sphere. This is the three-dimensional coordinate system with x, y, and z. X is coming out from the screen or the page. Now let us try to represent different points on this Bloch sphere. Here the Bloch sphere is our qubit state space. We may call it as the qubit state space. State space means it is the collection of states, and it is the collection of qubits. Qubits are used to represent state information. Now here we have already seen that the north pole is the qubit 0 and the south pole is the qubit 1. The x and y coordinate of the qubit 0 are means that z axis coordinate is 1, and for qubit 1 the z axis coordinate is -1. So this is the x, y, z coordinate for qubit 1 and qubit 0. So this is one way to represent geometrically the qubit through sphere. Now let us see here this point. Where the x-axis, this is our x-axis, and it cuts to the equator. The point at which x-axis cuts to the equator has the coordinate 1, 0, 0, and this point is called as a qubit plus, and its alpha coefficient, it is a superimposed state, it is not a pure state. Its alpha coefficients are 1 by root 2, and beta here, which is the coefficient that is associated with the qubit 1, is also reciprocal of square root of 2 or 1 upon square root of 2. So this is this point. This point is called as the qubit plus. Now similarly, the point at which x-axis, negative x-axis, cuts to the equator, that point we are calling it as the qubit minus, where the coordinate of this is x coordinate is -1, y coordinate is 0, and z coordinate is 0. Again, the alpha for this point is 1 by root 2, whereas the beta is -1 by root 2. So this point is the we are calling it as the qubit minus. Now let us denote some more points on this Bloch sphere. Now here what I am referring the point at the positive y-axis cuts to the equator. This is the point positive y-axis cutting at the place of equator. Now the coordinate of this point are y coordinate is 1 and x and y coordinate are x and z coordinate are 0. With this point is known as qubit I and its values, alpha value is 1 upon square root of 2 and beta values of are I times 1 upon root 2. Similarly, the point negative axis y-axis cuts to the equator. So this point has the coordinate x and z equal to 0 and y coordinate is -1. This point is known as minus I or qubit minus I. Its alpha coefficient is 1 upon root 2 and beta coefficients are minus I upon root 2. So it is not the case that a qubit always lies on equator or north and south pole. A qubit may lie on anywhere on this block sphere. Like for this example, here this is the point, which is not lying on x-axis or y-axis or z-axis or either on the equator, but this is the valid state of a qubit. Now, for this state, the alpha is root 3 by 2 and beta is 1 by 2. If you take the alpha square and beta square, it will be equal to alpha square plus beta square. It will come around to be 3 by 4 plus 1 by 4, which is equal to 4 by 4, which is nothing but equal to 1. So that's why this is a valid qubit state, which is not lying either on the x, y, z axis or on the equator. It is lying somewhere else on the Bloch sphere. Similarly, here I am denoting another point which is lying on the Bloch sphere and which is also a valid qubit state, and this point has the coordinates. This is the point represented as in terms of alpha and beta. Here alpha is equal to 2 by 3 and beta equal to 1 minus 2i by 3. If you take the summation of alpha square plus beta square, it may come around to be 4 by 9 plus 5 by 9 and which is 9 by 9, which is equal to 1. And that's why this is a valid qubit state. So that's why a qubit can be any point on the Bloch sphere. Bloch sphere is a powerful way of denoting a valid qubit state. So this is all about the quantum bits. Thank you.